the that tree and all those things. Okay. So let's we can do it using the last year's homework. Right? Last year's homework had a lot of type checking. This one. This is the solution or what? Pardon? Last year's homework. So go to this and homework 2 last year. Do not submit here. And this is the this year's second homework. So let's see. So this is. Let me change the code and try to do something with this. So let's discuss this first. Azure static scoping and Power BI. So, okay, no, I won't have it like this. So I'll say that. Let's make an example which is different from this. So include time into this tdio.h, right? And let's say you have a in B in C, right? And you are doing in X. Actually, I'm making it more complex than it should be. B plus C, and you return X. And in here in main, you have let's say you have in y, and you do y equals 4, 2, 3, right? And you return y. Let's say this code, and we want to draw the program stack at the first execution of location of it. Oh yes, it can return y also. It can return 0. So yeah, we need to draw the program stack. Now, what is the location? Which location should we draw? Let's say here. Let's say this is location 1, just before return. Here we need to draw the stack. So if we draw the stack, so our stack addresses are 0 here and some F here, right? Now initially we call main. So remember when we are discussing that other example, we had that the stack of the program that called main was somewhere here, right? The stack that the program of the program that called main. So whenever main is executed, the first thing that main does is that it pushes the EBP, right? So if it pushes the EBP, so let's say this is ESP and EBP will be somewhere here, right? So if it pushes the EBP, ESP should be now here, and this item should have EBP, right? So let's say this is EBP 0, this is ESP 0. Now ESP became here, EBP is this. Now what does the next thing main does? It moves the ESP to EBP, right? So this becomes EBP of main. This is EBP of main, right? This is EBP of main. Now what the main should do, it should create space for y, 2 and 3 at least. It might be space for more, but at least for the local variables and the variables 2 and 3, right? So it should create space for y, so maybe 1, 2 and 3. So it made 3 spaces at least, right? Then it will move 3, move this one, right? The last argument 3 first into the stack, and it moves it here, right? It moves 3 here. Then it moves 2 here, right? And y is here. That's what it does. So then the next thing that it should do is it should call foo. So if it calls foo, what does call do? Call also takes the next instruction. So ESP is now here, the new ESP. So when call gets called, it first pushes the instruction pointer into the stack, right? It pushes the instruction pointer. So the next, this is the EIP. So now stack is here, EIP is here. Then when you go to poly, so you go to foo, right? If you go to foo, then what foo does is that it also pushes the EBP. So what is the EBP of main? EBP of main was this one. So EBP, now stack again gets pushed back, and this becomes EBP of main, right? Now what is the entire stack of main? The entire stack of main is this part, and so this is the frame of main. This is the frame of main, and this is the, oh no, starting from 3. This is the frame of foo, right? So that is the frame of foo. Now what will foo do? Foo will create some space for x. It has to create some space for x. So at least it decrements by 1. At least. We don't know, it might do it for more. So this is for x, right? This is for x. Now what does foo do? Foo does b plus c. Now when it does b plus c, it doesn't really change anything in the stack. It just puts the number 2 into EAX, number 3 into EDX, and does LEA, right? So that does not change the stack at all. Now what it does, then x will have the value 2 plus 3, 5, right? X has the value 5. That is what happens. And then it return x. So what happens with return then? With return, what will happen is that it will first, I forgot what happens with return. You have to see the slide. Anybody remembers what happens with return? The exact sequence. I remember what all it does, but the exact sequence I forgot. Oh, okay. So what it does is that it will, so since it has created this variable, local variable x equals 5, it should call the function leave. It should call this assembly code because it has created some space. So leave, what it will do is it will immediately reverse whatever it changed in the stack. So first it will do this, and it also pushed EBP main, so it will also return the stack there, right? Then you call the return function. The return function does what? It pops the instruction pointer. If it pops the instruction pointer, it goes back here. The ESP goes back here, right? And then it also moves. The return also moves the BP to ESP. So EBP was basically we missed the step rather where ESP is moved to EBP. So yeah, this was EBP, right? This was EBP before. So now the EBP is to ESP, ESP moves back here, right? And the stack is clear. Now you don't have to talk about clearing of stack in your homework because that is not location 1. You don't really return, you keep on calling, right? So you don't have to worry about clearing of stack. What you have to do is just show this part. Just show what happens when you have call. Right? So if you can do that, then that should be fine. So here you don't need actual addresses. You just have some variables like EAP, EVP main, EVP0, or EVP foo, whatever you want to call it. Right? So you don't have to have actual variables. So when you do that example, do this.
Printf doesn't do anything to the stack, right?
It does, but I don't need you to show it.
Okay.
Printf does a lot of things with the stack.
But we don't do it.
Yeah.
So we're essentially just going down that
Yes, you don't have to go back. Just go up to x equals 5 and that should be fine. Any doubts on this one? So that is all I need for homework, that problem 3. Now actually this one is more complex than that one. Or maybe that one has recursion, right? Maybe that one is more complex. See which one is complex. So you should also let me know which ones are frames of main and foo.
And we show BSP and EV4.
Yes.
So is the frame just what contains the parts of that function? So like for main,
It's just the stack of that function. So for example,
Okay.
the main has EBP and Y. Now it has also pushed 3 and 2, but 3 and 2 are arguments of foo.
okay,
So that forms the part of the frame of foo. So frame of foo starts from here and it ends somewhere else. Now if foo calls another function, then it will have to push, like ESP will go down, it will have to push the instruction pointer, right? So then the other program's frame will start from here and foo's frame will end here. If foo called another function. The foo does not call another function, so this won't happen here. So that is one case. Yeah, take pictures. I will try to upload them. But
I can't read it from back.
is that EIP?
EIP. Instruction point.
Okay.
Oh,
Make sure you take my picture.
pardon?
Okay.
Yeah, don't take picture. So then that is one problem. Then other thing that we wanted to discuss was the type. So let's do homework 2. Okay, I will upload the solutions for this, but let's do one solution for the first problem. Um, So we have what? That is the function definition, right? So if we have function definition, that is the tree. So I will provide you the tree, provide you with the tree. So now what do? You have to apply the rules. So go back to the, so you have to remember the slides. What were the constraints? Okay. So let's see. F A B C. That's the function definition. So the constraint was ABC was one node and if was another node, right? So the constraint of function definition was What is the so if we have ABC, then f is a function. F is a function of types, type of A, type of B, type of C. So you give general types. You don't know the types yet, right? So you give type of A, type of B, type of C, and its return type should be the type of the expression E, right? Should be the type of the expression E. So if you make a table, initially you give general types to the to those. So if we have this um, this tree, this is if, right? Then you have apply. So initially you give a type that this is function of T1, or let's say TA, TB, TC, and return type is TD, right? Then you give this as TE. Then this don't need any return type. Then this is TF. No, TF. You can do a shortcut here because TF is same as TB, right? So this you keep as TB, TA, TC, TA, TC, TB, right? So initially you give all general types. Now you apply the constraints. So how will you apply the constraints? First you take that definition node. Definition node does not need a type. If ABC needs a type, it's TABC Now what is TD? You know that TD has to be the type of the expression, right? So you make this table. So you have TA, TB, TC, TD, then TE. That's it, TE. Then you have those variables A, B, C, D, and you have the there is no D, sorry. And you have the function f. So initially what you did was you have the types as these are all unknown types. TA you had it as TA, TB, TC, and this was function of TA, TB, TC. So this is how you represent it. TA, TB, TC, arrow, TD. Oh no, there was a TD. Sorry. No, TD is here. TE unit. Yes. Okay, so that was their function, right? Now initially you apply a constraint. So the constraint is you can come to this node, you say that the return type has to be the expression type. So TD has to be TE, right? So you made TD is basically TE, right? So you choose what to keep. If you choose to keep TE, then or if you choose to keep TD, then you make TD as TE as TD. Right? Depends on what you choose to keep. Then you come to that node if. What is the output of if? So if has to have a condition, right? So no, the output of if is either CA or CB. Right? So now CA or CB, all these things also have to have types actually because these are the return types, right? So you have furthermore. So if TF, TG, TG and TH, right? have to have types for them as well. So now you have TF, TG, and TH. Right? You come to if. So TE is TD, and the constraint is that these two have to be of the same type. So TG and TH have to be of the same type. That is the constraint. So TG, you choose whatever you want to keep. So let's say you want to keep TG. So TH becomes TG. It has to be of the same type when you are doing if. And TE has to be the same type as TG. The output of has to be the same type of TG. So choose whichever you want to keep. So let's say I want to keep TE. Now TE is TD, so I want to keep TD. So this became TD. And G also has to be TD. Right? So that is the constraint of if. There is one more condition, that the TF has to be Boolean. Right? There is another condition of if. So TF has to be Boolean. So this one is Boolean. Right? So by parsing that if node, you came to this conclusion. The TG has to be TD, TH has to be TD, and TF has to be Boolean. Now you go to that apply node. So you know that TF is Boolean, fine. Now this is a if condition. So you are evaluating a conditional operator. Now BA is a function, right? BA is a function application. So you come to B here. So B has to be function of something. So B is what? TB, right? So TB now is not really TB. It has to be function of something, and of something is what? B. A is the argument. So if A is the argument, it has to be a function of A, and it has to return something. It returns TF, right? So TF is bool. It has to return Boolean. B has to be this. By parsing the node B, you understood that. That B has to be this. Now if you come to A, you can't really do anything. A is TA. Right? There is no constraint there. Now you come to that second apply node, TG. You know TG, the output is TD, and this C is a function. So TC is not a TC anymore. It has to be a function of A. It's a function of A, and what is the return type? The return type should be TD. The return type should be TD. Then you again parse A, you don't see anything, nothing changes. You come to that next apply node. You see that the next apply node is also a function of C. Now C is already TA goes to TD, right? So if the the TB is what? TA goes to Boolean. And C is taking TA. So there is a conflict here. Right? So A is of type TA. B takes the type TA and gives Boolean as output. And C is it takes in the type of B as well as type of A.
Which are you looking at? Are you looking at which branch? The middle branch.
The third
branch.
branch.
Oh, okay.
The third branch. So now C is a function of A as well as C is a function of B. How do you justify that? Can you justify this in any way? Or is there a type conflict?
Could you explain how? So you're saying C is a function of B, and C is a function of
So C's argument is B.
right,
We're seeing the third node.
right.
If you see the third node, C's argument is B. If you see the second node, C's argument is A. Right? Now A has a different type. A is type TA and B is type, it takes TA and outputs bool. Right? So if C is a function of B, then what does it mean? That C should take an argument.
Whose type
So B is a function. Right?
Yeah.
B is a function.
Right.
C should take an argument whose type is bool. Right?
Okay.
If C takes an argument whose type is bool, then that means TA has to be boolean.
And it's not? Is that what you're
No,
saying?
it's not. It's a general type, so you can make TA boolean.
Okay.
Right? So TA has to be boolean. If TA is boolean, then no, let's not do TA is. Then this C becomes takes in a boolean and outputs TD. This B becomes takes in a boolean, outputs boolean. Right? So TA is boolean, so that means this is boolean. TB is what? TB is takes in a boolean, outputs a boolean. TC is takes in a boolean, outputs TD. TD we cannot resolve to anything. That's it. We have parsed all the nodes. Right, so this is how you do Hindley-Milner. One example. Yes.
What was the final answer?
This one.
Just the table?
Just the table. So you draw the tree and you give general types to everything. Now in the table what you do is you do type inference and show what is the exact value of those general types.
And so you could leave TD.
Yeah, you cannot resolve TD any further. So you keep TD like that.
And really quickly, that's an A, obviously, right?
Which one?
For type of A, like the very last row of the branches. That's an A, not a C, right? So
Which one?
TB and then TA, right?
This one?
No, go for the left. That's an A, right?
Yeah, that's it. Okay, so that is one example. The other examples, I'm not doing them again. I will. What I will do is I will just post the solution. Do you want me to discuss anything else? Anybody wants to discuss anything else?
Would you be willing to go over structural equivalence again?
Structural equivalence. Which can you give? Do you have an example?
Not on hand. There's one on the homework you can do like you did with the first one we did. And
So
do something
you have
similar.
structural equivalence here, right?
Yeah.
I cannot show this one.
Okay.
In the slides, we had an example.
Yes.
If I redo that, or maybe a variant of that, let's see. Type systems. This one was our example, right? So let's redo, do another example maybe. T1 is struct, let's say A is T5, no, T4. Let's say A is T4 and P is a pointer to T2. Let's keep it simple. Then T2 is struct C is in and Q is O. And there is T3 which is struct B as a function. Takes T2 as input, returns in. Say R. T4 is takes T2. Okay. I've tried to make it abundantly complex. I don't know whether it's complex or not. Let's see. So what we'll do, we have to find structural equivalence between T1, T2, T3, T4. I don't know the answer. Let's see. So you make the table T1, T2, T3, T4, T1, T2, T3, T4. Initially everything is true. T1 you don't need to check. T1 T2. Let's check T1 T2. What is T1? T1 and T2 are both struct, so we have to apply the type checking rules for struct, structural equivalence for struct. So what is the deal here? Structural equivalence to struct means that these two have to be structurally equivalent. Right? So T4 has to be int. Right? Now T4 is if T4 is int, the T4 is a general type, right? So we don't know whether T4 is int or not. So we will assume that, let's say T4 is int. We don't know whether T4 is int or not. So we will assume that okay, let's say T4 is int. So we assume T4 is int. Now then the next one we say that okay, Q is T4 and P has to be a pointer to T2. Now if Q is T4 and T4 is int, Q cannot be pointer to an int. Right? Q is not a pointer. So but P is a pointer. P is a pointer, right? So if P is a pointer, then these two are not structurally equivalent. Because you know P is pointer and Q is just an int. Q is a T4. Does not matter whether T4 is int or not. Does not matter. T4 is not pointer. Yes? You wanted to say something?
So that's false.
Yes, that's false. Yes. So T1, T2 are not equivalent. Now let's say if T1, T2 is not equivalent, T2, T1 are also not equivalent. False. Right? Now let's say T1, T3, right? T1, T3. Now it says A, B, right? So T4 now has to be a function of T2 to int, right? T4 has to be a function of T2 to int. And we know that T4 is a function of T2 to int. So that is fine. P and R has to be pointer to T2, pointer to T2. Yes. So T2, T1, T3 is true. T1, T4. So T1 is a struct, T4 is a function. T1, T4 is false. So if T1, T4 is false, T4, T1 is also false. Now let's check T2, T2 has to be true, T2, T3. Let's check T2, T3. Now structure, C is an int, B is a function. Immediately false, right? So T2, T3 is false. So if T2, T3 is false, T3, T2 is also false. Then let's check T2, T4. T2 is a struct, T4 is a function. No. So T2, T4 is also false. T4, T2 is false too. Then T3, T2 we have already checked. T3, T3 we don't need to check. T3 and T4. No, T3 is a structure, T4 is a function. So this is also false. Now it has changed, so you have to check again. If you check again, you will see that it remains the same.
Why was T2, T3 false?
T2, T3, okay, because they are both structures. This C and B has to be of same structural type. So these two are not structurally equivalent because this is a variable int and this is a function.
But I thought, yeah, it goes to.
That's fine. It returns an int. That's fine. But B has to be a function. On the other hand, C is an int. It's not an application. Remember, it's not an application. This is a definition. In definition, you cannot have. You should not match the return type. In the previous Hindley-Milner type checking or type inference, we said that okay, since the return value is the same, so TA has to be Boolean, right? Why could we say that? We could say that because it was an apply node. It was not a definition node. If it was a definition node, we couldn't have said that. Because that is not the constraint of definition node. But the constraint of apply node says that whatever is the value of that application, or whatever is the value of the expression, the return value of the expression becomes the type of the apply node. Right? That's why we looked at the return type, because it's apply node, not a definition node. Now here it's definition. This is not application. This is definition. So since this is definition, we cannot say that these two are equivalent. Structural equivalence. That's one example. Anything else you would want to discuss? We can discuss the final exam, but have anybody tried the final exam? The sample finals? So I'll let you try. Maybe tomorrow I will discuss the final exam. Do you have any other questions that needs discussion?
Did you ever reach a decision on the distribution of for the weight of the projects?
So for me, I have told you the distribution. Do you have any other suggestions on the distribution? If everybody agrees with the distribution that I have decided, then that's fine.
Was it the k-means?
No, not the grade. I'm saying the distribution, as in the weightage of the assignments and homeworks and exams. Is the weight fine? The weight that I have, that
Well,
assignment 1, 2, 3 each have 10%, homework 1, 2 each have 10%, midterm has 20%, final has 30%.
So for the first project, it was 35 points. So if you assumed that it was only going to be worth 35, you didn't.
If you assume what?
If you assumed that it was only going to be worth 35, then that would hurt you.
It's not only going to be worth 35. That's what I'm saying. So it has equal weight. So that means the whatever marks you have gotten, you divide it by 35, multiply it by 10. So then that's equal weight. So you see, you think about it. If you feel that I need to change the weights, tell me beforehand. Maybe tell me by Friday. So you discuss among yourselves, right? You discuss among yourselves. You come up with a weight. Then we'll discuss that weight on Friday. If it seems reasonable, I'll keep that weight. If it seems absurd, I won't keep that weight. Right? So what you do is you probably let me open up a discussion forum. I'll open up a discussion forum. You discuss, and you give me. You have to come to a consensus. You come to a consensus, and you give me a weight. Then I will see whether that weight makes sense. So pre-decided weights are each assignment is 10%. So total 30%. Then each homework is 10%. So total 20%. Midterm 20%. Final 30%. So now you discuss you want to change the weights or not. But you have to come to a consensus.
So
Anybody disagrees is not going to work.
So we could come up to consensus on any distribution, any weight.
You can come to a consensus on any weight, but then I will decide whether to keep that weight. You guys, but the only constraint is that none of the okay. So let me put a constraint. None of the components should have 0 weight, and total sum of weight should be 100. Yes. These are the constraints. So following these constraints, you come up with the weight distribution. But you have to agree on it. If somebody gives a strong objection, then I won't keep that weight.
Could we take a vote on Friday just to see if everyone?
You can do that. So I submit, you discuss.
So if you were to go to my grades right now,
My grade?
yeah, if you were to click the grade book.
I cannot pick because it will show all everybody's grade.
Oh, okay. Because I was gonna say there's like if you click view details, there's already like that pre-decided thing. Would that, like the curved grade points, is that still in effect, or is that also decided with the total grade points minus 100 plus max?
No, that is also under discussion.
Okay.
So basically that is not really a big deal to discuss. I will see. I will do all of the ways and see which one is better.
Okay.
Any other thing you want to discuss?
Can you talk about the symbol table for
Yes.
this project here?
Symbol table for project 2.
Yeah.
Project 2 symbol table I already uploaded. The lecture.
But I don't understand. Oh, you mean the code?
Yeah, cool.
But I want to understand what is symbol, like how to implement it. If I
For
already.
project 2.
Yeah.
But project 2 is already done.
But I want to know.
Oh, you want to know? So, okay.
Did you so the one that you posted has the correct implementation of the symbol table or not?
Yes.
Oh.
It has a working symbol table, but it does not say where to add, where to delete.
Oh.
It does not say that. It says that you could add to a symbol table, you could delete, you could update scope, but when to update scope, when to add to a symbol table, when to delete, it's not there.
So for project 3, are we allowed to use that symbol table?
You
Is it
can
not-
use that implementation of symbol table.
Did you give us the search function or no?
Yes, the search list is also there. But I just don't say when you search, when you add, when you delete. Right? So when do you do that? There are a few places where you would add into a symbol table. First of all, so with respect to project 2, so this is not project 3, right? But similar things apply to project 3 as well. So if you have a definition like this, public a int, right? Oh, in project 2 you did not have int, just a. If you have this, then when you come to this is variable declaration, right? You are declaring variable. So the moment you declare variable, you add an element in the symbol table. So what you add? You add the variable a. You add its value. Value here is nothing. You don't have. Oh no, type, right? Type here is nothing. You don't know really what is the type. So you do question mark, and then whether it is public or private. So 1 or 0. So here it is public, so you have 1. Right?
In assignment 2, we needed scope, not type.
Oh, scope. Yes. In assignment 2, you need that scope.
That's
So-
good.
Yeah. What?
You can go ahead a little bit.
No. If I do scope, then that type is different. Type you won't do it this way, right? If I want to discuss type,
And do the test case 16.
what?
Test case 16. That means
What
a test case 16.
takes case 16. Then you come to my office hours.
Okay.
I cannot discuss the exact test case now. I can give you the algorithm. So okay, let's discuss
For
scope
type-
and we'll discuss type later.
Okay.
Right.
Because it would be, yeah.
So scope, you say that, okay, let's say this was a scope test, right? So whenever you come to scope, then you keep current scope, you update current scope, and you make a current scope as test. You come to a public variable, basically have this here. Put the current scope there. So create a symbol table entry that has the variable name A, and it has the current scope here, and it has whether it's public or private, right? So whenever you encounter a variable definition, you keep on including in the symbol table. Variable definition, right? Now in assignment 2, all the variables were defined. There were no implicit declarations, right? So that becomes easier. Now when you want to search the list, so let's say you have an assignment A equals B, right? You have an assignment. So here, let's say you had C and D, all public, right? C and D. So you have C, current scope is test 1, D, current scope test 1. Now you encounter the assignment A equals B. So you have to, the moment you encounter an assignment, search the list. Search the list with what key? You search it with A, the name of the variable. So the key for searching has to be the name of the variable. Right? So you search using A, you see that no A is not equal to D, so you search this. No A is not equal to C, you search this. Yes, you found A. You saw that the scope is equal to current scope, so you can use it. Whether private, public, you don't need to check private, public. So you can use it. So what you did was you printed out, okay, A. I forgot the format. I think test.a, right? Test.a. Then you enter the equal to, yes. You now use B. You search B, no B, no B, no B. In the entire symbol table, there is no B. So then you put question mark dot B. Now let's say you encounter a closed brace. If you encounter closed brace, you know the current scope test. What you do is now search using test. Search using test, right? And delete all the variables that were that has scope test. Delete all the variables from the symbol table.
That's not, yeah.
So that is for assignment 2. That's how you manipulate the symbol table. Do you understand now? Anywhere else you do? No, nowhere else you manipulate symbol table, right? No, so there is another case in assignment 2. So let's say this was test and you had another outer scope which was main. Let's say you had an outer scope which was main and you had a variable b which was private. No, so variable b was private. So you have a private b, right? So if you have private b, then initially you pass that scope. So you will have b here, main, and 0, right? So when you search b now, you will see that no b, no b, no b. Now you found b, right? You found b here. Now you see that okay, current main is not equal to current scope. If main is not equal to current scope, check the public private. You saw this is private 0, so you cannot use it. You search again. Yes.
Just really quickly, so in another scenario, you could not do top down also, right? You could have, say, within that scope, you could have B declared after that last brace at the bottom, or the second to last brace at the bottom. That would be
Where?
perfectly
Here?
fine.
No, in assignment 2 you don't have such
I know,
cases.
I'm just saying, generally speaking, that would be
Well, that will be totally different. cost.
top down.
Then you won't have, you cannot have this type of implementation. This type of implementation works by assuming that particular grammar. So that is for assignment 2. Now how do you do assignment 3? Right? So assignment 3, there we didn't have scope, we had type. So in assignment 3, there can be 2 cases where you add into symbol table. In assignment 2, there was only one case that you declare, you add into the symbol table. But in assignment 3, there are 2 cases. First, you can declare. You can declare a variable, then you add it to the symbol table. Second is you don't declare, but you have it in an assignment statement, right? So if you have it in an assignment statement, then if you don't see that B is not there anywhere, then you have to add B, right? So this is slightly different scenario. So in assignment 2, if B is nowhere, you didn't find B, right? So you say no B, then you have to add B. B, you don't know the type, public, private, you don't care here, right?
Yeah.
So you have to add B. So those are 2 places where you need to add B if you don't find B. It's the same thing as assignment 2. You whenever you have an assignment statement, you go search symbol for A and B. If you find A, very good. If you don't find A, very good. You add A to the symbol table, right? Now you have to do type check or type inference. Now how do you do type inference? So my theory is in assignment 3 you did need to do very small changes to the assignment 2 that you have done. Not a lot of changes. First of all, you have to change the parser. That's a big task. It's a big parser. The parser is quite easy, but I have already given you the parser. So you look at the code and do the parser. So that is easy. So once you have the parser, then you use that same symbol table that you designed for assignment 2, and so you can use that symbol table for all variable declarations, because that you already have in assignment 2. You have already added variable declarations into symbol table. The only thing I have to change is that whenever you parse an assignment statement, so in the parse assignment function, in parse assignment statement function,
Our statement. Right? or statement?
No, it can be E for while. Statement can be E for while.
Oh,
So E for while is slightly different from assignment. Here, if you see the parser that I have uploaded, I have separate functions for assignment, separate for if, separate for while.
okay.
So when you go to the parse assignment statement, what you do is for each assignment, again you do the same thing. You search the symbol table. So same thing as assignment 2. You search the symbol table. The only difference being if you do not find a variable in the symbol table, you have to add it to the symbol table. You just don't say that not found scope is question mark. No. Now you have to add it to the symbol table, right? Not only you have to add it to the symbol table, you have to write a function that checks the types. Right?
Yeah.
You have to write a function that checks the types. Now, what can be different cases for types?
You could have, yeah, what types? You could have a lot. You could have long, float, double.
No. Those types are defined here. You
I
can only
understand.
have some specific types.
Yeah.
You
Scroll
can
back
only
up.
have what type?
I
Where is
think
it?
you scroll back up, I think. or-
What? No, this one. Int real code. Only 3 types.
Oh.
Right? You can only have 3 types. Now, so if the type is not defined, then you have question mark, right? So let's say, let's take some example, then we'll be more clear. Let's take let's do those examples. So here you don't need to keep track of scope. Nice. Okay, so this one. So you first encounter a, b, int. So you have a declaration. So the moment you have declaration in the symbol table, you add, okay, a is a variable, its type is int, you immediately know. Then here you add b is another variable, its type is int. No need for scope. Right? You don't have to have scope. Now what you can do is instead of having strings here, you can give unique numbers. Right? So if you don't know the type, you give it -1. Int can be 0, real can be 1, boolean can be 3. So you are not doing string comparison. Right? You are just doing number comparison. So you have this. Now you come to this assignment. A equals less than B2. Right? That's what the assignment is. So you come to this assignment, you see that this is A. Well, let's search the symbol table. You found, okay, B is not A. There is an A. And its type is int, right? So there is an A. So immediately you can format the string that you want to print. That what is the output format? A colon int star int hash, right? So immediately you formatted the string that okay A int formatted the string. No, what you can do is while you are so you already know that A B int. Whenever you are uploading to the symbol table, you can format the string. You don't have to format the string whenever you are doing the assignment statement. If the variable is declared, you know, right? So immediately you found the string. So you found one string, then the another string is this one, right? You have already found this string. Now you come here, you see that A is int, you know A is declared, then equal to, right? So this is an assignment. Now in assignment, you know that left hand side has to be equal to right hand side. It has to be equal to right hand side. So you know that you can keep two variables, LRH type and right hand side, LHS type. Sorry. you can have two variables for assignment statements, LHS type and RHS type, right? So first of all, you see A, you found A in the symbol table. Immediately you make LHS type as int. Right? Now you go to this. Now next is an operation. So you parse. You go to the parse binary operation function, right? In binary operation, you are expecting two variables. So B, you have expected B, right? So in here, the moment you see B, you again search the symbol table. You say that, okay, I found B. B is an int. So again, parse binary operator has E1 type, expression 1 type, and it also has to have an expression 2 type, right? So in here, you say, okay, E1 type is int. You understood. Then you next parse the second. This is a constant. Constant is 2. So you say that, okay, E2 type is int. Then the last line of parse binary, before you return, you say that, okay, E1 type is equal to E2 type. You have an if condition. E1 type equals E2 type. If this type is fine, then you say, okay, no, the return type, or you can have some return type in parse binary, which is maybe an integer. So you say that the return, that these two types are fine, but less than returns bool, right? So bool is 3, so that means return 3. So parse binary operator return 3. Now if parse binary operator return 3, then you say that, okay, RHS type is bool. So int had the type 1, the number 1, bool had the number 3, right? So return type is bool. Now when you are parsing the assignment, in the parse assignment statement, what you do is, after parsing, parser is already there. After parsing, you again check if LHS type is equal to RHS type, then type OK. So have some variable that says, okay, type OK. Right, type OK equals true. Else, say type mismatch. And you format the string the way you format type mismatch, the type mismatch 3, and then C1 is the code, because LHS is not equal to RHS. So what you really need to do is, in each of those parse binary operator function, have these modules that check types, even these modules, right? That is all you need to do for assignment 3. Now, what if it is not declared? In this case, it was fine. What if it was not declared, right? I will. Okay, let me take it. What if it was not declared? So, what if you had
Are all the test cases declared?
pardon?
All the test cases have been declared, right? Or
No, there are some test cases where it's not declared. So, what if it's not declared? A and B is not declared. So, you don't have the symbol table there. Now, you come here, you see A, search symbol table, empty symbol table. You have to put A there. So, you put A there. You don't know the type. Type is -1. Then you come equal to. So the moment that happens, then LHS type is equal to -1. Right? Then you come to equal to, and then you do parse operator. Oh no, parse binary operator. Okay? So in parse binary operator, you see again, you search for B. You see B not found. So if B not found, then you have to add it. Add B. Now you don't know the type of B. So you add B here. B minus 1. Right? Then you go to the next number. Number is 2. Right? Number is 2. So 2 is of type int. So then what you do is, since B so you had E1 type is equal to minus 1. Then you say that okay, E2 type is 1. Right? Now you know that E1 type is minus 1. So it is neither 0 nor 1 nor 2. Right? It's unknown. Let's keep 1. Not 0. Neither 1 nor 2 nor 3. 1 is for integer, 2 is for real, 3 is for boolean. Right? So neither 1 nor 2 nor 3. So if E1 is minus 1, if E1t is equal to minus 1, then what you do is you make E1t equals E2t. Right? You make it equal. E1t equals E2t. Because it's unknown type. So there won't be any type error. You can change it if it's unknown type. So if E1t equals E2t, then here you have to update the symbol table. Make it 1. So it was minus 1 previously. Make it 1. Change it to 1. Right? Now once you change it to 1, you return that this is less than, this is boolean. Right? So this is boolean. So you had RHST equals 3. Then you say that okay, if LHST is equal to minus 1, this unknown type, then LHST has to be equal to RHST. Now you know that LHST was type of A, so A's type became the type of A became boolean. So if type of A is boolean, then you have to go back and change the 1 to 3. Right. So then you output that it is bool. No, sorry. A is bool. B is int. That example is not there. So that is the module that you need to use. You already have the parse functions, just implement the type module. You already have the symbol table. That is assignment 3. Any questions on this?
Will you post that image you took online?
I will try. It's taking long time to upload the videos, especially.
The format AVI.
What?
The format, how large is it?
It's MP4. Each video is taking 3-4 hours to upload. And either I need to reduce the quality or buy a new camera. But that will happen next semester. Okay, any other questions? If you don't have any other questions, I want to go a little bit early. You send
Since all of that's zero, yeah. Actually makes sense.
Not even.